Guideline Geo webinar. Today we're looking at protocol choices for 2D electrical resistivity tomography surveys, and the webinar will introduce choosing a suitable array, talk about the structure of spread and protocol files, and then demonstrate the process of creating 2D spread and protocol files using the free ABEM companion software called Terrameter LS protocol tool. The webinar will take approximately 1 hour to complete. And if you have any questions during, please enter them into the chat, and we'll try to answer those at the end. Just to introduce myself briefly, my name's Harry Higgs, and I'll be your host for today. I started off in geophysics, studying my undergraduate degree, and then working in industry in the UK as a near-surface geophysicist for about 7 years, and then joining Guideline Geo in 2021 as an application engineer. And here I provide sales and technical support to our customers. So to begin our webinar, each set of measurements using the Terrameter LS2 requires the choice of both a spread file and a protocol file. So the spread file describes the cable and electrode layout for the instrument. It gives an electrode ID number and an XYZ location for each. And each electrode ID is linked to a pin number, which is connected to the electrode selector switches inside the Terrameter LS2 or the ES1064 external switch matrix. Then the protocol file describes the type of electrode arrangement. It lists the spread files that are compatible with it. And it lists the sequence of current injectors and voltage measurements using those ID numbers that are taken from the spread file. So the protocol file defines the measuring sequence. But before we look more closely at how spread and protocol files are created and how they operate, we should first answer the question of how we would choose a suitable spread and protocol file for a particular survey aim. So this goes back to the planning stage, and so we should briefly touch on this first. And ultimately, these planning steps will help us to answer what type of method and, if applicable, array is suited, and from there allow us to choose a protocol. So firstly, we need to define the problem, and that should ultimately answer the questions of whether resistivity is suitable for the problem at hand, what information is available from the site, and can we expect to have a resistivity contrast from that targeted structure? If we decide that resistivity is suitable, then the more specifically we can define the questions that the survey needs to answer, then generally the more successful that survey will be. So for example, if we know what we're looking for and we know how that will present itself in the data. So for example, if I'm looking for an air-filled void and therefore looking for confined areas of increased resistivity, then we can concentrate on that particular aspect of the data first and foremost and design our survey around those targets. So the type of target will help us to decide which type of array to use. We should also consider that there are different arrays during the planning stage. For example, Venner, Schlumberger, dipole, and gradient. And all of these electrode arrays have different sensitivity. So dipole, for example, has a strong vertical sensitivity, whereas Venner and Schlumberger have better horizontal sensitivity. The sensitivity of gradient is mixed depending on where the potential electrodes are situated relative to the current electrodes. So on the right-hand side, we have sensitivity plots for those electrode arrangements, where red and orange colors indicate positive sensitivity and blue's negative sensitivity. And these are showing where the electrode arrangement is most sensitive to resistivity change, where the resistivity in the ground is giving the highest contribution to the result that you measure. Because we need to remember that the potential field is everywhere, current is flowing pretty much everywhere. So for a single arrangement of electrodes, we are not measuring a discrete point in the ground. We are measuring a volume of earth that the current is passing through. And to generate a pseudo section as a way to represent that value, we put that at a point in the ground. We put this at what we call a focus position, but in reality, we're looking at a large volume. And so these plots show you where within that volume, the majority of the result that you record would be coming from. And because Venner and Schlumberger are uniquely symmetrical, because they expand around the central point all of the time, and what you can also see is that the sensitivity on something like the Venner and Schlumberger is not very narrow, it's quite broad and drops off relatively quickly with depth, whereas an array like the dipole-dipole or gradient is narrower in its region of higher sensitivities. So that automatically starts to tell us what kind of features they might be better suited to. So Venner and Schlumberger are good for horizontal layers. With dipole-dipole, because its sensitivity has that vertical component, it's better for locating vertical structures. And gradient is a good compromise array because current is injected on the outside between the A and B electrodes, and then the potential pair will take readings on the inside. And in places where the potential pair is closer to the A or the B electrode, the sensitivity is closer to vertical. And when that potential pair is more central between A and B electrodes, the sensitivity is more horizontal. Gradient is not as good as Venner or Schlumberger for horizontal, or as good as dipole-dipole for vertical. But unlike the others, it does have a good sensitivity for both types of structure. So if you're not sure about the target, or the target has aspects requiring sensitivity in both directions, then gradient can be a good choice. And when survey planning, we need to consider the size of the target for the electrode array we are using, and if we have enough resolution to successfully image it. In a resistivity imaging system, the resolution is related to the electrode spacing. The vertical resolution is considered to be better than the horizontal resolution. At the surface, theoretical resolution is approximately half of the electrode spacing laterally and 1/4 of the electrode spacing vertically, but we can still only predict those values for the very near surface. Resolution decreases with depth. This is true with all geophysical techniques, regardless of whether we're discussing transient electromagnetics, seismics, GPR, or resistivity. Generally, you can have shallow and detailed surveys or deeper but low resolution results. So it's impossible to predict the exact resolution at depth, as it will vary depending on the geology and the subsequent current paths. But the inversion software can give us an impression of the theoretical resolution. The inversion software builds a model of ground resistivity, and it does this by dividing the ground into a series of blocks or cells and assigning a resistivity to each of these blocks. And then it runs a synthetic survey over this model and compares the results to our real-world data. And the model used for the inversion increases the cell size to reflect the likely resolution as we get deeper into the ground. In this diagram, the X markers indicate focus positions for measurements in one of the Terrameter's measurement protocols. And what does this mean for building protocols? Well, it means we need more measurement points or focus positions in the shallower parts of the model where the array has more resolution, and fewer measurement points or focus positions in the deeper parts of the model where the model blocks are larger. So in the left and the right images are gradient array pseudosections showing focus positions with dots. The color relates to the size of the geometric factor. In the left image, all possible measurement positions are used. And on the right, the number of the focus positions have been limited to a few per model block. So the methods we will discuss for limiting or controlling the distribution of measurement positions are key to building efficient protocol. And depth of investigation, that's going to be primarily governed by the length of our cables, the distance from the first to the last electrode, but also to some degree by the choice of protocol. Maximum depth also changes depending on the array type used. So Venner has the poorest ratio of electrode spacing to maximum depth. And out of these four, dipole-dipole has the best ratio of distance between electrodes versus maximum depth. This table is an example of the statistics for some of ABEM's protocols for different arrays. The thing we're interested in at the moment is the depth factor in the right-hand column. This depth factor describes the relationship between the total cable length and the maximum depth. So if the total cable length was 100 meters, the maximum depth for a Venner array would be 100 times by the depth factor 0.16, which would give 16 meters. And for dipole-dipole, it would be 100 times 0.22 or 22 meters. The rule of thumb for these arrays is investigation depth equals approximately 1/5 of spread length. The other thing to think about is that vertical resolution is a little better with arrays like dipole-dipole and gradient, because we can have more focus positions that are closer together vertically than we can with Venner. For example, with Venner, as we expand our electrodes, it has to be symmetrical, and that means we end up with some large increments in depth level as you expand those electrodes. Therefore, you are limited on how many unique depth levels your focus points can sit at. And for pole-pole, there are some electrode arrangements that you may or may not have come across, pole-dipole and pole-pole, and you can see their depth factors are very good. You can see much deeper for a given spread length. However, there's some caveats associated with using such electrode arrangements. So the pole-dipole array requires one of the current electrodes, the B electrode, or the C2 as it's also known, to be placed at a remote location. The geophysics textbooks say this remote location should be 20 times the maximum space between your remaining current electrode, labeled A on the diagram, and your potential electrodes M and N. So for example, with a 4x12 spread and 20-meter electrode spacing, if electrode 1 was used as the A electrode and A and M were the electrodes 47 and 48 on that spread, the distance from A to M would be 920 meters, and that would require the remote electrode to be 18.5 kilometers away. And even if we use a value of 5 to 10 times the A to M distance, the remote electrode would still be 4.6 to 9.2 kilometers from the spread, which is a lot of cable to use. And another aspect in choosing a protocol is time constraints. This is a big problem for commercial operators and also on the academic side. Limitation on how long you can be on site will influence the way that you set the instrument up. And that can affect things like how long you make the current pulse or how many stacks. But also another thing that we can look at is the type of array that we're using. So Venner and Schlumberger arrays are single channel arrays. And as I said before, uniquely symmetrical. So you define your position of current injectors, and that basically defines your single focus position that defines the current flow in the ground and why that sensitivity is focused in the half space. Your voltage pair are always at the center of the spread then, and only one, and the only difference between Venner and Schlumberger is that they're always equally spaced with Venner and Schlumberger. With Schlumberger, they're slightly closer together, but ultimately there's only one location that your electrodes can go. There's only one focus position that you can achieve with those 4 electrodes whilst you're injecting current. So if I was to move the voltage pair closer together to maintain the symmetry, so to go from a Venner here to a Schlumberger, that focus position wouldn't shift. So I'm still measuring the same point in the ground. I can't put another pair of M and N anywhere else because then that would no longer be a Venner or a Schlumberger. So you can only collect one data point every time you inject current. If you use something like a dipole-dipole or a gradient array, then we're talking about multi-channel arrays. So the example here is a dipole-dipole. Current is being injected on one side at the A and B electrode. And whilst the current is flowing there, we can measure voltages at different locations along the spread. And the limit on how many voltage readings we can take is based on the design of the instrument and how many channels it has and how many electrodes are available. In other words, am I going to run out of space on my spread cables before I've used all of my available channels? So that means if you've got, say, 300 or 400 readings to take with your Venner or Schlumberger array, then you've got to inject current 300 or 400 times. So that's at least 300 or 400 cycles before we start to look at the potential for stacking measurements. That's repeating them several times to improve signal to noise ratio. Whereas for dipole-dipole, for example, I might be able to do 1,500 readings, and I might be able to do that with just 150 current injections if I've averaged 10 channels per current injection. So it massively speeds up data collection, and that's why things like dipole-dipole and gradient are very commonly used for electrical resistivity tomography, and Venner and Schlumberger are more commonly used for VES. So what can we say now about our list of pros and cons that we're building for each of the arrays? Well, now we can say that Venner and Schlumberger are only single channel, and dipole-dipole and gradient are both multi-channel. Another consideration, environmental information and likelihood of noise. So how much electromagnetic noise is there likely to be within the environment that we're working in? And environmental noise is coming from all sorts of different sources, from lightning to mobile phones to TV, radio transmissions, and it's inducing voltage into the ground. So if we're in an urban environment, this is likely to be a larger issue and something that we can consider when choosing our array type. Current flow is in a nested array looks like this. As most energy flows between the current electrodes, the voltage reading on the potential electrodes are usually reasonably high. Therefore, you end up with an excellent signal to noise ratio, and this includes Venner, Schlumberger, and gradient arrays. Current flow in dipole-dipole array is shown here. It's getting weaker and weaker as the potential electrodes get further away from the current injectors. As parts of the current are absorbed by the ground in between the current and the potential dipole, the voltage reading on the potential electrodes can, as a result, be very small, especially if the distance between the dipoles is large. So now going back to our list, we can say this about the signal to noise ratio of our principal arrays. That Venner has the best signal to noise ratio. Schlumberger has a very good signal to noise ratio. Dipole-dipole has a relatively poor signal to noise ratio compared to the top two, and multiple gradient has a relatively good signal to noise ratio compared to dipole-dipole. And if, for example, it would be great to use Venner, but I don't have the time to be on site for particularly long, or I know that I want to look at voids, but I'm worried about the amount of noise on the site, well, then you could potentially use a mixed array. And so a mixed array is one where we change the combination of electrodes during the survey. So this is an example of what might be our starting point, and this is created using the free spread and protocol tool. We would have a protocol which is here full of Venner measurements, for example. So you can see equally spaced electrodes, which give us sort of coarse outline of points. But we could then ask the system to add in different electrode arrangements or focus points that use different arrangements that bring other benefits to the survey. And what we can say is that we can either just add those in as extra measurements, or we can ask it to only add in those extra arrangements to pre-existing current injections. So for example, we could ask it to add some gradient measurements into here. So whilst the current is being injected on the outside, and this particular Venner point has been collected, we could fill in some of the extra potential pairs that would be in a gradient arrangement that would then give us the ability to map more confined structures within that space. So a mixed array allows us to make a dense data set, which is more efficient because we're using current injectors that already exist. So no extra measurements, and hopefully give us a better final model because we're able to collect using arrangements that respond well to different targets. And if we do have mixed arrays and we don't think it's been particularly effective, or we think that actually one of the array types could be causing an issue, so say we put dipole-dipole measurements in and they're really noisy, when you come to export the data, you can actually choose which arrangements to keep and automatically discard other types. So you don't need to worry about the fact that maybe you have actually had any kind of detrimental effect to the data set, because you can also filter those out afterwards. So now we know what considerations are needed to decide which method and array type to use. We can begin to look at the format of the spread and protocol files. So the files are in XML text format, so they're very simple to use. You can view these files easily and make changes using XML marker software. On installation of LS Toolbox, spreads and protocols are written to the file location shown here. So this software comes with a bundle of existing spreads and protocols that are saved into this location. And LS Toolbox will look into this file location when transferring new spread and protocol files to the instrument. You can also remotely log into the instrument if it's connected to a network using free file transfer software like Windows SCP. And these options are described in more detail within the user manual and support documents. And once we've uploaded our spreads and protocols to the instrument, we can select a spread file from the task menu. Then only compatible protocols will be listed. Electrode positions in the spread file are unit spacing. So that's to say that they're always 1 unit between adjacent electrodes, and true spacing is entered as a multiplier in the task menu. So that's to say that the minimum electrode spacing given in the task menu is multiplied by the unit spacing given in the spread file. And let's say we want to set up a new spread file. By way of example, here's a typical 2-cable setup with the instrument in the center of the spread. We have the side panel of the Terrameter LS2 shown here. The first connector connects to switches 1 to 32. The second connector connects to switches 33 to 64. The spread file requires that we define a switch address for each electrode. This is fixed and based on how the cable is wired internally, i.e. which pin on the cable and therefore pin on the instrument does each individual strand of wire from a takeout connect to. Then we give each electrode an ID, and these values will be used by the protocol to select individual electrodes for current or potential use. And these can be any user-defined values, but normally they are numbered from the left to the right along the spread, as is shown here. And then finally, we have the takeout name. This is the label shown in the electrode tab on the instrument and the table of results. Again, this can be user-defined, but commonly it follows the format of cable number followed by takeout number. And note that the cables have takeout numbers written on them, so they would typically follow this same numbering to avoid any confusion in the field. When creating a spread file, we also add in the relative position of each electrode with the x coordinate for 2D spreads. the X and Y coordinate in 3D spreads. And if working with borehole tomography, then that might also read in X, Y, and Z coordinates. And we're just looking at 2D spreads today, so we need to only define the X location. And remember, this spread file is usually written with a unit spacing of 1. Then when we access the spread within the Terrameter, we select the true electrode spacing for the particular spread that we're using on site. And now looking at how a particular electrode is defined within the spread file. For example, for the 5th electrode along the spread, there'll be an ID value. For the 5th electrode, this will be a 5. And it'll have an X location of 4, since we have one electrode at 0. And then we have the name, which is 1-5, so cable 1, electrode 5. And then we have the switch address, which is 5. And for electrode 21, we have the same logic, and 42, and cable 60. And this shows us now how each electrode is defined along that spread. And those bits of text, they just sit in a single file as a long list within our spread file. So let's just quickly look at the spread files in a little more detail. So if you were to open a spread file and look inside of it, first we would have some XML header information. And then we would have the start of the spread description and spread name. The name here is shown in the instrument menus. So if making a new spread file, the text here is what defines the name shown in the Terrameter user interface. Even if the file is saved with a different name, it's important to update the text within the spread file itself, because that's what is linked to what you see on the Terrameter LS user interface. And then we have a description. So that description is shown in LS Toolbox in the spread and protocol dialog. So that's just the description of the spread file itself. And that's manually written. Then we have our station information. So we create stations for roll-alongs as well as stationary positions. So we have these listed. We have some old compatibility style formatting that will go in there as well. And then we go on to define the cables and the electrodes themselves. So the first thing we do is we define a cable and give it a name. And then we start to define all of the electrodes that sit within that cable. So that's, as we saw on the last slide, where you give the ID, the X location, and the name and switch address. You do that for all of the electrodes that sit on that cable. And then you would define any of the cables that are in there. And for a protocol file, it's very similar formatting. So we start with some protocol information. We give a protocol name, and again, that's shown in the LS2 user interface. We have a description for that protocol file. We have an array code identifier that's used with res2d and res3d inv. We have a list of the compatible spread files for that protocol. And then we list the sequence of measurements that we want to take. So we start with what we call a measurement group. And then we define the TX electrodes. And these are the IDs that are written, that are read from the spread file. So we have the TX defined, and then after this we have the receiver pair defined that will go with that measurement cycle. And if it's a multi-channel measurement, then you can have more than one receiver defined. So you would list all of the receivers that are associated with that measurement. and then you would close that measurement group off, and you would start a new measurement group. So starting a new measurement group, again, just listing the transmitter and the receiver pairs for that group. And then once you've done that with all of the measurements, we just close the sequence to indicate the end of that sequence. And then the end of the protocol. So that concludes the presentation side in PowerPoint. So I'm just going to go and show a quick demonstration creating a mixed array using the spread and protocol tool. Okay, so you should all be able to see my screen now. So this is the LS protocol tool. This is designed to enable users to develop customized spread and protocol files from scratch. So to create a spread file, which is the first thing we want to do, we go to our general overview and we click work on spread. And using the number of electrodes per cable, we can adjust this to the number of electrodes we want. So we will use 32. And we can just left click on the instrument icon and add a cable to the left of the instrument, and then left click on it again and add a cable to the right of the instrument. There are checkboxes for remote current Z2 or remote potential P2, which we talked about if we were doing pole-pole or pole-dipole. If you're adding only pole-pole measurements, then the pole-pole plug can be used. This restricts the measurement type to pole-pole, but it does allow you to use 12 channels for each measurement. But we won't be creating one of those today, just to be aware of. What we do need to do is create some stations. So we want to create a two cables no move. So this will just be when you first lay out the two cables in the field and you first start your first measurement sequence. So for this, we'll have no station shift. It will just be as you lay it out, and we just press add new station. But then if we want to produce a long profile and do that by the method of roll along, where we pick up one cable and move it forwards and then move the instrument forwards one cable length as well, then we'll need to have roll along stations. So we can make one for rolling forwards and call this one cable forwards. And that will have a station shift of 32 electrodes. Add as new station. And we'll also have one station, one cable backwards. And that would be if we wanted to roll in the reverse direction by one cable. And we can also go into the individual cables here and look at the active electrodes. And here's where, if you wanted, you could change things like your X location for electrodes, Y location, and switch address that have been automatically assigned. You also can toggle electrodes and also reverse cables. So if you had a mirrored array where you had the lowest numbered takeouts closest to the instrument when the instrument is in the center of the two cables. So with the takeout numbers increasing as the cables move away from the instrument, you would need to have your first cable set up so it was a cable backwards. So you have options for that as well. But now that we've set up our basic spread file, we just need to save this. So we just click Save Spread. Then we give it a name, and this is the name that will be saved into the spread file and the name that will appear on the Terrameter LS2 user interface. So I'm going to call this 2 by 32 increasing to signify that the takeout numbers are increasing along the both cables. Spread description 2 by 32 electrode spread if takeout numbers increasing and to the other. That's okay. And I will just call this 2 by 32. If we were just very quickly to look at the format of this. So we see that our name is that we defined as we saved it. We have the description entered here, and then we have our 3 stations that we created. So 2 cables, so no move, 1 cable forwards, 1 cable backwards. We have the old style compatibility that we mentioned in the presentation, and then we go straight into defining the cable and all of the electrodes that sit within that first cable. And then we have a second cable here, cable number 2, and all of the electrodes that sit within that cable as well. And then the end of the spread file there. So now that we've created a simple spread file, we also want to create protocols for it. So let's look at how to do this in a way that should allow for some degree of channel optimization. So what we want to do is go back to our general overview and click Work on Protocol, and then make protocol from scratch. And it will automatically be working with the spread file that's loaded in. So if you open this up and you don't have a spread file loaded in, you'll have to load one in or make one for it to be able to make a protocol. So the first thing we want to do is add measure points to our protocol. So I'd like to make a mixed array and begin by adding Venner measurements. So we add point types here, Venner, and this brings up a menu to allow us to restrict the number of data points. So if we don't apply any restrictions, so that's to say that we don't make any adjustments in this menu, and we just press apply, the software will try to add all possible measurement combinations. And this could lead to a very time-consuming protocol to acquire data with in the field. So when we add measurements, we have a variety of tools for controlling where in the pseudo section measuring points are added. We can do this by turning on limit data points to pseudo section blocks, which is this button here. And this subdivides the pseudo section into blocks, much like the inversion model does. And then using the sliders, we can adjust the height and the width of those blocks. We can also set minimum and maximum limits for the admissible geometric factors. And we can limit the number of measurements allowed per pseudo section block. And then when we add the points, you'll see that they're either red or green or somewhere in between. And those colors are related to the geometric factor that's associated with that focus position. So as I say, let's begin with adding a number of Venner measurements. In this case, I want to produce a distribution of measuring points that will match the Res2D Inv default model settings. And in Res2D Inv, the model blocks increase with a depth factor using a factor of 1.1 per layer. the block widths stay the same. They are the width of the electrode spacing, and the first layer thickness is set to the minimum pseudo depth of the data points. So to kind of mimic this, I'm going to start with a base width of 2 in here, which gives approximately 1 model block between each electrode. If I press update, we're going to have a base height scale of 1.1. We're going to have a block width increase per depth step of 0, and a block height increase per depth step of 10%. We're going to have just 1 point per block, and we don't need to have any channel optimization for this because it's just Venner. If I press show, and there we have it, we will add this kind of distribution of measuring points, 438. I'll press apply here. And then what I'd like to do is add in dipole-dipole measuring points to this. So we go back to our add point type, press dipole-dipole. So if we have a multi-channel instrument, we can make use of the unused channels by selecting the option add RX pairs to existing TX pairs here. So once again, we want to limit our data points to the pseudo section blocks, and then also add RX pairs to existing TX pairs. So by activating this option, the software will look at the current injection points used for the existing Venner measurements. It will look at the unused electrodes and the unused channels, and it will then create a list of possible dipole-dipole measurements that can be added. Because we opted for no new current injections to be created, the measurement time will not increase, providing that none of the measurements are split within the split matrix, switch matrix. And we can also apply restrictions on where the measuring points are distributed within the pseudo section in the same way that we demonstrated previously. So I'll follow a very similar setup with this, with using the base width of 2, a base height of 1, block increase with depth of 0, and a block increase in height with each layer of 10%. But this time, we want to select the optimization number for the number of channels that the instrument has. So this will attempt to distribute the measurements over the switch matrix to prevent the measurements being split over multiple current injections. So I'm going to use an 8-channel optimization, but I'm also going to increase the maximum amount of points per block to 5. So that's added 929 new points. And what we now have is a dense pseudo section of mixed array measurements. We can now go back and add more data points using the same menu if we want to, using a different array type if we wish. Or if there's a gaps that we want to fill, we can double click an individual data point and calculate nearby data points that the switch matrix has room to add measurements for. So I'll just apply these. So we can see here that there are a few gaps towards the edges. If we click on an individual data point, up on this top row here, we can see the individual electrodes. Half are red because they're on cable 1, and half are yellow to show that they're on a separate cable, cable 2. So if we have the highlighted data point in teal here, it will show you that the electrodes that are in use to create that focus position. So the current electrodes are in blue on the outside, C1 and C2, and the 2 inner electrodes that are highlighted are in green, and those are P1 and P2. You can see the distance between each is equal, so we know that this is one of the Venner measurements, and the instrument hasn't actually added any other measurements on this injection cycle for this particular point. But what we can do is left click on it and then right click, and then we can select 8 channel optimized points to add to that TX pair. And it will calculate where you could have additional data points. So let's just add one out to the edge, where we could do the same for this side. And when we click on that, we'll see that now we have an extra measuring point. Another thing that we can do if we want to work on our pseudo section a bit is you can see that this doesn't quite come down into a full triangle point. So if we click on some of these IDs out here, we're not quite using the furthest electrodes that would give us the very deepest measuring point. And we can either do that by when we're adding the points at the start by just adjusting the geometric factors slightly up and down, just to try and get that distribution a little bit more even or a little bit deeper. The other thing we can try is to add in a custom pattern. So if I go to add in a custom pattern, I just want to get the top bar blank. What you do to add a custom pattern is you just left click on these electrodes in here, these blank electrodes, to draw in what you want the pattern to look like. So first you use a left click to denote where your C1 would be. So you can have a C1 here. Let's try a C2 here. And then and then the next 2 clicks will be our P1 and P2. So P1 here, P2 here. And then we also have to have, you have to click a couple of times on the adjacent pair, because what we can do is we can get this to repeat the measurement all the way along the spread if we want to, along multiple depth levels. But we just want to have a couple of points. So that'll just add in a couple more measuring points at a slightly deeper level. So once we've completed this process, the next step is to press the finalize data generation button, which is here. This brings up a few more options, including the roll along gap optimization. So if I click on that tab here and just start that running. So what this is, if the current has been sent through an electrode, and then that electrode will remain polarized for a period of time after the current has been turned off. And if an electrode which is still polarized is used as a potential electrode, it can have a negative influence on the data quality. So we want to schedule the sequence of measurements so that there is a resting period after an electrode has been used for a current injection, and before that electrode is then used in a different measurement cycle to measure potential. So the protocol tool has an algorithm that reorders the current injections to optimize the gap length, and this is what you're seeing occur right now. So the lists labeled first run data quality and second run data quality show the execution order of the protocol's current injections. So that is, in a roll along setup, the first run data quality are the current injections of the first station that is set up in the field, and the second run quality lists the subsequent injections where the terrameter has been moved forwards one station position. The individual rows contain the entries called, you'll see a TX, and then the current IDs of the current electrodes are listed, and then RX, and that gives the set of electrode IDs of the potential electrodes. And then after that, you see gap quality, which is importantly the number of measurements that occur until one of the TX electrodes is utilized as an RX pole. So by example, gap quality of 0 would indicate that an electrode is used as a potential electrode directly after it has been functioning as a current electrode. And we have a slider on the right-hand side called accepted gap length that specifies to the algorithm above what limit the gap lengths are not considered worth moving. So by default, this is set to 6. But the definition of an acceptable value highly depends on the measurement parameters used during field acquisition, but the algorithm will generally work with a large range of values. So even for a standard protocol, the algorithm can run for a very long time. It's therefore possible to stop the process manually by pressing the stop button if an acceptable quality has been achieved. Once the user saves the protocol, it will be saved with the sequence order from the latest gap optimization. So I will stop this running now. When running gap optimization, the process can be monitored via the overall quality measure, which is shown here just below. And this indicates how well optimized the protocol is with respect to all of the gaps. And this number will decrease as the algorithm progresses. A number in the range of 20 to 40 will indicate a pretty well gap optimized protocol, where there are a few but not many gaps of length 2. Such overall values should be obtainable for most protocols. So now we've created our protocol. We have run the optimization on it. So we're now ready to save that protocol. And again, the protocol name is the name that will show up on the Terrameter LS UI. And I'm going to try and keep the name quite short because there's a limit to the number of characters that you can easily see on the screen of the Terrameter LS. So if we make a very long name, sometimes you can lose some of the characters at the end. So it's good to keep that condensed where you can, but then with the protocol description, you can write something longer. We can just quickly look at this format. Again, this is the name that we entered when we saved it, the description, the spread files that are compatible with this. So we've only selected one spread file, but if I just quickly go back into here, under File, you can link spread files to a particular protocol if you have more than one spread file that are compatible with a protocol. So those are listed here. You then have your array code that's used by Res2D or 3D-Inv, so 11 general array, and then you're followed straight into your sequence where you have your measure, and then your TX defined using your electrode IDs from the spread file, so 5763, and then below this you're receiving poles, so 5961, and it's telling you which channel that's going to be recorded on. And you can see we have 1, 2, 3, 4, 5, 6, 7, 8. So it's using all 8 of the channels that we specified with the optimization to record. So 1 of those will be Venner, and 7 of those will be dipole-dipole. And that just continues all the way down. It won't always be possible to have full optimization because we've limited our data points in the pseudo section, partly, but also partly because of the switch matrix itself. But because we've limited our distribution of data points, primarily that's why we won't have full utilization. So that'll be all the way to the end of our protocol. So that's the structure of that, and I'm just going to pop back to the presentation very quickly. So just briefly in summary, the best choice of spread and protocol really depends on the type of target that you are looking for and the site in which you're looking for it. So the environmental factors as well will play a part. We looked at the spread and protocol files, and we've seen that they follow just this simple XML format, and they can be manually edited, but also it can be put together by using the protocol tool, which is a relatively quick and efficient way to make use of multi-channel functionality.